I think we can begin. So welcome to the Tests of General Relativity with the Third Gravitational Wave Catalogs webinar. We're happy to have you here today to learn about what new results were put forth in this work and to be able to ask questions to a team of panelists who were involved in the analysis. On the lower left of the screen here, you'll be able to see some places to find more information about the paper. So if we go to the next screen. So today what we're going to do is you're going to hear from the paper writing team of the Test of GR paper. I'll be the moderator. My name is Deirdre Shoemaker. Arun will tell us about the introductions and conclusions of the work. Jenny will give us a perspective on the data and some of the events. Harris will discuss consistency tests. Marta will tell us about tests of generation, propagation, and polarization. Krishnendu will speak about tests using the remnant black hole. Then we will open things up for you to ask questions of the panelists. The panelists were the people involved in the analysis, of which there are many in the paper. So you'll hear from Peter, Apertim, Jan, Gregorio, Epirup, Anna, and Isaac, and you're welcome to ask them questions. I will have the question and answer window open, and we'll do our best to answer things live, but we also might answer in the chat if we have too many questions. So the way this webinar has been organized is basically walking through the paper. So you'll hear the introduction, then the general about the data, then the discussion of the various tests of GR before we conclude. And now I'll leave it to Arun to begin.
Yeah, hi. So I will talk about give you a broad introduction to the topic, though many of you would be experts. So it's good to recall in this context, as we are talking about tests of GR using compact binaries, what are the different stages of its dynamical evolution. We have the early in-spiral, which is well described by post-Newtonian approximation. The late in-spiral and the merger requires you to deal with numerical relativity simulations to get an accurate description of the dynamics. And the ring down of the remnant black hole, especially in the late stages, is well described again by the black hole perturbation theory. So these are the broadly three regimes, and you will see very many tests talking about various aspects of this in the slides to come. At the bottom, you can get a typical velocity. So you can see that when these black holes merge, they merge at a speed close to that of light. So what we are seeing are actually relativistic collisions, if you can call, of compact binaries. And this indeed gives a new, unique opportunity to test the validity of GR in this extremely strong field and radiative regime. So what we are expecting is that if there are beyond GR physics signatures, it should show up as a modification to the dynamics, and which we can track through the waveforms. We can track whether the dynamics is indeed consistent with the predictions of GR. So we search for deviations using different types of searches in some sense, which will be reported in the coming slides. So before we go to that, it's good to stress that the approach that we take here is what we can call as theory agnostic, in the sense we do not rely on the predictions of alternatives to GR. Instead, we make use of the best knowledge of GR, and we look for deviations about GR or deviations around GR, and we will constrain any possible deviations from GR. So these are often referred to as null tests about GR. And in terms of the various tests we perform, they may be very broadly classified as consistency test and parameterized test. And the consistency test itself could be a self-consistency, because it could be consistency between two parts of the waveform that we saw. Or it could be overall consistency of the signal with GR, the signal in the data with GR. And the second category comes with a specific, we introduce free parameters which model certain aspects depending upon the context, how the deviation could occur in those contexts. And these additional parameters which we introduce could be constrained using gravitational observations during various stages. So through this test, we probe the generation, propagation, and the polarization of gravitational waves from the various stages of the dynamical evolution of the compact binaries using the third observing band, the second half of the third observing band. So with that introduction, I will give to Jenny, who will explain about the O3B and some of the selection criteria and a broad introduction to the events that we analyzed. Over to you, Jenny.
As I hope you've heard from several of the collaboration's other webinars, the gravitational wave detectors that we operate have been increasing their sensitivity greatly as time has gone on. And so this new catalog adds a total of 35 new detections, each of which has a probability of being truly astrophysical better than 0.5. This plot shows on the x-axis time in days that we're actually operating. So maintenance and installation periods have been excised. And the y-axis is cumulative number of these detections with p astro greater than 0.5. And you can see that the third observing run has been wildly successful, including the second half of the third observing run, which is what we report on here. So if we go to the next slide. Of those events, we look more closely, in particular, at 35 events with an inverse false alarm rate of better than 1,000 per year. So we take the kind of most likely 15 events from that set. Of those 15, 14 are binary black holes, and one in particular is a neutron star black hole coalescence. The table on the right, table 2 from the paper, lists out the names and details of these 15 events, including what instrument was involved in the actual detection, some parameters such as their masses and luminosity distance and spins. Each of the different analyses that Arun was alluding to has separate sub-selection criteria to get the most out of the test that they're able to do. So the far right side of the plot indicates which test uses which of the events in it. And to provide a much more rich data set, whenever possible, we do combine our events with the previous gravitational wave catalogs. If we go to the next slide, please. Before we can do, or as part of doing these tests of general relativity, we need to understand the astrophysical aspects of our different events. We use as the basis for kind of starting things different waveforms for each of the different analyses. These are typically general relativity waveforms to which deviations will be added, as Arun was talking about. So we have two different classes of waveforms that we typically use. With those waveforms, we also use some standard LIGO Virgo Cagra parameter estimation tools to determine the actual astrophysical parameters from those waveforms. And following our previous tests of general relativity papers, we provide two types of bounds. In addition to providing bounds for each individual event, we combine the bounds between events to try and get better constraints on deviations. The two different assumptions that we make and present are deviations can take the same value for every source, and we call that the restricted deviation assumption combination, or we also present results where deviations can be different for each different source, and that is the hierarchical combination. So we combine our events together among both the third catalog, and then where possible, we also fold in those events from the second catalog. So with that, I'll hand over to Harris to discuss the first class of tests.
Thanks, Jenny. The first category of our test is a consistency test. So here we check for the consistency of the detector data. So there are two tests in this category, and the first one is a residual test. In the residual test, we check whether the residual data, which is obtained by subtracting the best fit gravitational wave form from the detector data, are consistent with the expected detector noise. For this, we compute coherent SNR in the residual data using model-independent base wave pipeline. So in ideal scenario, like the The only coherent part of the data, which is coherent among all the detectors, is the gravitational wave signal. Therefore, the coherent power in the residual data is expected to be low, very low. We further perform a set of background analysis around each event to assess the significance of these computed coherent SNRs using p-values, which is the fraction of the coherent residual SNRs, a fraction of coherent residual SNRs for the background above the foreground SNR. We performed this analysis on all the 15 events listed in the previous table, and we use IMR Phenom XPHM model for this analysis. In this slide, we have a summary of the results from this analysis. The left-hand side plot is a scatter plot between GR SNR, that is the gravitational wave SNR, and the residual SNR of individual events, with the color bar denoting the corresponding p-values. So as you can see, there is no particular trend between these two SNRs, that indicates actually the residual SNR is coming completely from the random noise. So in the right-hand side, we have a PP plot of the p-values of these residual SNRs. Here, the diagonal dashed line is the null hypothesis, with light gray band around the null hypothesis denoting the uncertainty band due to the finite number of events. And the blue line is the PP plot of the residual SNRs, with the light blue region denoting the uncertainty, 90% uncertainty region. As you can see, they agree well, indicating the agreement of the data and the GR template used for the analysis. Next slide, please. So the next test in this category is IMR consistency test, that is in-spiral merger ring down consistency test. Here we check the consistency of different part of the waveform. Basically the in-spiral region of the waveform and the post-in-spiral region of the waveform. For this, we estimate the mass and spin of the final black hole using in-spiral part of the waveform and post-in-spiral part of the waveform separately, and check whether these estimates are consistent or not. For this, we define two deviation parameters as given in the equation, and then we check how the posteriors of these deviation parameters looks like, or whether they are consistent with 0. So for this analysis, we have used IMR Phenom XPHM waveform, and the parameter estimation is performed using the Bilby pipeline with the dynasty sampler. Next slide, please. In this slide, we have the main results from this analysis. We perform this test on 5 events. The choice is made based on the SNR of these events in spiral and post-in-spiral region. So in the right-hand side, we have the corner plot of these deviation parameters. The colored contours denotes the posteriors for individual events, with gray contour denoting the combined posterior. So as you can see, like these contours are consistent with 0, indicating no deviation. Next slide. So we further combine these results with the results from the previous analysis. And in the figure, what we have is the histograms of the combined results. Those are represented by the solid blue and red histograms. And we also shows the results from the previous catalogs, that those are GWTC-1 and 2 in different shades, just for comparison. And as you can see, the histograms are consistent with 0, indicating consistency with GR predictions. Next slide. So now I'll hand over to Martha to discuss the test on gravitational wave generation. Thanks.
Hi, everyone. Thanks, Haris. Yes, so I will guide you through the next batch of tests. We have two types of tests of gravitational wave generation. The first type looks for generic modifications to the phasing of the gravitational wave signal. These generic modifications could arise as a consequence of the presence of additional fields or higher order curvature corrections, introducing alternative theories of gravity. The second type of test is more specific and is targeting spin-induced quadrupole moments. And this test leverages the idea that different compact objects will deform as an effect of their rotation, and they will develop spin-induced deformations based on their internal structure. And if we measure these effects, we could learn something about the nature of the compact objects that are merging. So we look for imprints on the gravitational wave phase of these two modifications. So let's talk about the first test. Here we focus on the in-spiral part of the signal. And we ask ourselves, is the in-spiral phase consistent with general relativity? So as Arun mentioned, the in-spiral part of the signal is well described by the post-Newtonian approximation. And in this framework, we can write the gravitational wave phase as a power series in terms of the frequency, with each order being referred to as a PN order. And we introduce individual deviations at each PN order, so one at a time, and then compute posterior distributions for these deviations. Besides the PN coefficients that are already present in GR, we also add generic modifications at -1 PN and 0.5 PN order. The -1 PN term will be non-zero in the presence of dipolar radiation, which is forbidden in general relativity. We compute posteriors for individual events and then compute joint bounds on the deviation coefficients, combining all the new events that Jenny showed earlier with the ones analyzed in past papers. So as a baseline for this test, we use a specific waveform model, SUB and RV4-Rho, and we introduce deviations in the phasing of this model that are then smoothly turned off after a certain frequency cutoff that we pick in the in-spiral part of the waveform. And then we reparameterize the results as deviations in the non-spinning terms of a 3.5 PN Taylor F2 phase, for which we write the formal expression here so that you can see. We introduce relative deviations if the GR term at that specific PN order is non-zero. Otherwise, we work with absolute deviations. And you can see that we have a series here with different phasing coefficients phi. And each order will have a certain scaling with the frequency, with more negative PN orders being more important in the first part of the in-spiral, and higher order terms becoming more important towards the end of the spiral. So here we show the first plot for the results of this test. We combine the deviations from GR measured for each event, and we compute 90% credible upper bounds of the magnitude of the deviation coefficients. Here we simply multiply the individual likelihoods of individual events, and we assume, therefore, that the deviation coefficients are the same across all events. So we observe here in this plot the new results that are plotted as blue filled diamonds, and they are compared to the results presented in the previous paper, which are plotted as either filled or empty diamonds in gray. We can see that there is an overall consistency with previous results, although there is a marked improvement in the bound on the -1 p.m. term, which is mainly driven by the inclusion of a neutron star black hole candidate. This is a very long signal that helps tightening the constraint at this order. So next slide, please. Here we see instead the posteriors for the same method applied in the previous slide, shown together with the posteriors obtained with a different combination method, which is the hierarchical method. Here, as Jenny said earlier, we assume that the deviation coefficient can have arbitrary values, can be taken from distribution. So this is a less restrictive hypothesis than the earlier one. And we show the posteriors obtained with this method in blue, whereas the ones obtained with the joint likelihood approach are shown as unfilled curves. For the first method, we also show the median as a y-dashed line and the 90% credible interval with horizontal ticks. And again, we see consistency with the GR prediction, as all posteriors have support for the GR value, which is 0. In the next slide, we see we introduce the second type of test of gravitational wave generation. As I said, spinning objects will deform as an effect of their rotation, and this will leave a direct imprint on the gravitational wave waveform, which enters at leading order as a 2 p.m. effect. So you can see here that this effect can be is encapsulated in this quadruple spin-induced quadruple moment, which is proportional to the square of the spin, and is parameterized by this kappa. Kappa is exactly 1 for pure black holes. This is simply telling us that the multipolar structure of space-time is uniquely determined by the spin and mass of the black hole, which we expect from the no-hair conjecture. But for other objects, say neutron stars or boson stars, this kappa can take other values, can be positive or even negative for exotic objects like Grava stars. And in this slide, we introduce the deviations that we actually constrained in the analysis. We introduce parametric deviations in each spin-induced quadruple moment parameter. So in principle, we will have 2 deviations because we have 2 objects merging. But since these parameters are highly degenerate with other source parameters, it turns out that it's much better to constrain the symmetric combination of these 2 parameters. And we further assume that the antisymmetric combination of the 2 vanishes, which means that we take the 2 parameters to be the same. So we introduce these coefficients, these deviation coefficients in IMR phenom PV2 waveforms and run the analysis to constrain possible deviations using Lal inference. So here on this slide, we have the results of this analysis. On the left-hand side, we have the posterior distributions for the delta kappa S. So we set the deviation on the symmetric combination of the spin-induced quadrupole moment parameters for each event that passes the selection criteria for this test. And on the right-hand side, we have the combined results for this deviation. We have two curves because as for the previous test, we have two methods. One is the joint likelihood approach, which is the red curve. And the other one is the hierarchical combination method, which is the blue curve. Here we see that 0, which is the value that we would expect if all objects observed will be black holes, falls slightly outside the 90% credible intervals for the red posteriors. This is a consequence of the correlation of delta kappa S with the effective spin of the source, which means that typically we constrain better positive deviations for the type of sources that we observe. We also compute log 10 Bayes factors, comparing the Kerr black hole hypothesis to alternative hypothesis. And we see that, again, the Kerr black hole hypothesis is supported by the data, especially when we constrain the delta kappa S to be positive. Otherwise, we have rather uninformative results. On the next slide, so here we move to a different type of test. We will test how gravitational waves propagate. So gravitational waves in general relativity propagate non-dispersively at the speed of light, but there are modified theories, for instance, massive graviton theories or generic Lorentz violating theories that predict dispersion of gravitational waves. And if there is dispersion, the different frequency components of the wave will travel at different speeds. So for instance, radiation emitted in the Erwin spiral will travel more slowly. And this will affect the overall morphology of the signal, leading to an effective dephasing that can be measured and can be modeled. This dephasing affects, more importantly, distant sources because it scales like the luminosity distance of the source. So it's a cumulative effect. How do we test the presence of dispersion? We introduce a parameterized dispersion relation where we correct the dispersion relation that is valid in GR with a phenomenological correction that is proportional to a power of the graviton's momentum, and is also parameterized by a certain deviation coefficient A alpha. And then we compute posteriors and bounds for A alpha for different values of alpha from 0 to 4 in steps of 0.5, where 2 is excluded because it would just amount to a global time shift of the signal. From this expression, we can also see that if we calculate bounds on A0, when A0 is positive, we can also convert these bounds into bounds for the mass of the graviton, which is given by this expression in terms of our parameterized dispersion relation. As I said before, we model this as a dephasing, which we add on top of IMR Phenomex P waveforms. And then again, as we do for many tests, we compute combined bounds from several events also taken from past analysis. Here we show the results of this test so we perform the analysis separately for positive and negative deviation coefficients A alpha. So on the left-hand side, we showed the full posteriors for any sign of A alpha, which we obtain by combining the results of the two analyses. And on the right-hand side, we show the 90% credible upper bounds on the absolute value of these deviations for each of the two analyses. So here we show in gray results from GWTC-2, and in blue or red results for the new analysis. We have two colors because we have two different subsets of events combined here. So we can see that, especially from the plot on the right-hand side, that on average, we do improve our constraint on these deviation coefficients with respect to GWTC-2. And remarkably, we also obtain an improved bound on the graviton mass with respect to that analysis, which is also more than 2 times better than solar system bound. Next, we move on to tests of gravitational wave polarizations. So in a general metric theory of gravity, we will have up to 6 polarization modes for gravitational waves, to tensor, to scalar, and to vector modes. And with a network of interferometers, we can probe the polarization content of gravitational waves, because detectors at different locations will have a different response to gravitational wave signals depending on their sky location of the source and on the polarization content of the signal. Here we use a method based on the concept of null stream. A null stream is a linear combination of detector outputs, which contains no gravitational wave signal, assuming that the polarization hypothesis we are working with is correct, and is waveform agnostic. And as I already mentioned, if we perform this projection and we find the residual is consistent with noise, then the polarization hypothesis we are assuming is likely to be the right one. Here we present the main results of these analyses. One of the big differences with respect to past analysis is that here we test for the presence of pure but also mixed polarizations. This is possible because the new method we employ is based on a null projection with respect to a subspace that is spanned by basis modes, which can be either 1 or 2. And this subspace does not need to coincide with the subspace corresponding to the hypothesis being tested. So it's a constrained subspace in a sense, and we can leverage this fact that we are working with a lower dimensional projection operator to use also all events, even two detector events only. We combine all eligible events from 1, 01, 02, 03 to get stronger bounds and compute log10 base factors, comparing different polarization hypotheses. So pure polarization hypotheses that are not tensorial, like scalar or vector, against tensorial, and the same thing for various types of mixed hypotheses. So here on the right-hand side, you see two tables. One is for the one basis mode analysis, and the other one is for the two basis modes analysis. And so here we have circled the main result, the log10 base factor. You can see that all these numbers are either negative or small, which means that there is no support for alternative polarization hypotheses in the data. And now I'll hand over to Krishnendu for a discussion of the test based on the ring down.
Hello, everyone. Thanks, Martha. So now we are moving into the final test set of tests performed in this presentation, which are mainly based on the Remnant properties. So as you can see, or we discussed in the introduction, when you have an spiraling compact binary system, it merges to form a remnant black hole. And this highly distorted space-time emits gravitational wave called as the ring down radiation. And this ring down can be expressed as quasi-normal modes, as schematically represented by this equation. Moving on to next slide. So when we closely look into this equation, set damped sinusoidal with an amplitude and phase in terms of spherical harmonic representation, and you can also see the LMN values, and N here represents the overtones, and L and M are different modes, representing different modes. And here the spherical harmonics SLMN are functions of the polar angles theta phi and the final spin of the black hole chi f. And the main important two quantities we are interested here are the damping time of the mode tau LMN and the oscillation frequency FLMN. So if we are finding, or if the remnant object is an astrophysical black hole in GR, these frequency and damping time are characterized by the mass and spin of the black hole. And this is also often termed as the final state conjecture. So from the observation of the ring down radiation, gravitational observations, we can actually probe this conjecture by measuring these remnant black hole properties and do a test of the nature of the remnant object. And this method or the analysis is called the black hole spectroscopy. Moving on to next slide. So in this presentation, we have two different kinds of black hole spectroscopy analysis. The first one I'm discussing here is the Pyring analysis. And the Pyring is a gravitational wave data analysis toolkit designed to perform both parameter estimation and model selection of gravitational wave ring down radiation, which is a Python-based toolkit implemented in time domain. So in this analysis, we mainly have three different template models to perform this ring down analysis, which are KER220, KER221, and KER-HM. So as you can see from these equations representing different templates, KER220 only has the fundamental mode, that is L equal to 0 and M equal to 2, and KER221 also has the first overtone, that is the N equal to 1, and KER-HM has all the higher modes with L less than equal to 4 with the first overtone. So using these three template models, we do a parameterized ring down analysis, particularly looking for any observational evidence for deviation from general relativity by modifying this KER221 template. And also we do a parameter estimation analysis of the properties of the final black hole using these three template models, and also do a Bayesian model selection analysis assuming these three models, comparing three different hypotheses. Moving on to next slide. So in this table, the main results of the Pyring analysis is tabulated. So the first column lists all the events considered for this analysis. And as I mentioned earlier, the second two columns represent the measurements of the redshifted final mass and final spin of the remnant black hole using 4 different templates. The first one is the full IMR template and the 3 new ring down templates, KER220, KER221, and KER-HM. And as we discussed earlier, so we can also do a Bayesian model selection problem using these different template models. So the first set of base factors we quote here is the base factors which look for the presence of higher modes present in the signal, that is HM220. And the second type of base factors we have are looking for the presence of overtones present in the data. And we also calculate an odds ratio, which is actually a weighted sum of different base factors which look for parametric deviations in the GR model at the KER221 template. And these base factors values, from these base factors values, what we can see is that the remnant black hole properties we infer from these templates, the KER220, KER221, and KER-HM are consistent with the one we infer from the full IMR template. And also, we don't find any evidence for higher modes, or the base factors we see are not very significantly showing evidence for higher modes. And also, as you can see, we see very less significance for the presence of overtones in the data. Moving on to next slide. So this is next type of analysis we do is by introducing a parametric deviation in the ring down frequency and amplitude using the Curve-221 template. So the delta F221, which is plotted on this plot on the left side, is the deviation introduced in the F221 frequency parameter. So the distribution here shows two different curves. One corresponds to our previous results, that is the dotted blue lines coming from the GWTC-2 events, and the solid lines, which are the red solid lines, corresponds to the events which also include the O3B events, which is represented by this label GWTC-3. So these histograms are obtained by hierarchically combining the results from all the events. And I also denoted this dotted line in the middle, which represents the GR value. And as you can see from this plot, that the GR value, which is well inside the 90% bound, which is marked by these vertical bars, indicating that we don't find any or the findings we have are consistent with the GR prediction of the model. Moving on to the next slide. So the second type of black hole spectroscopy analysis we do is based on the parameterized SUB model. So from the this analysis is based on the SUB NRV4 HM waveform model, and this model can predict the frequency and damping time given the initial masses and spins of the binary system. So as I shown in these equations, this F and tau again represents the frequency and damping times respectively in terms of the component masses and spins of the binary system. And in the parameterized SUB model, where one introduces a parametric deviations in the frequency and damping time in the following way. So what we do here is we measure these deviation parameters along with the GR parameters using the Lal inference sampler algorithm, and constrain these parameters from the data for the events which have certain SNR both in the in-spiral and the post-in-spiral regimes. Moving on to next slide. So here, this is the main results from this analysis. On the left side, this is a contour plot. The main results are the contour plots of the delta F220 and delta tau 220. These are the frequency and damping times of the 220 mode. And the contours represents the 2D posteriors on these deviation parameters, and also you can see the 1D posteriors on both sides of this plot. And to highlight a few cases which give good constraints on this test, we also give them in the colored contours, and you can also see these light lines which corresponds to all the other events analyzed for this test. And dot dash lines here again represents the hierarchically combined results, and you get this gray distribution when we combine the results using likelihood multiplication, or assuming that equal deviation for all the events analyzed. And on the right plot, the 90% bounds on these fractional parameters are shown separately, highlighting each event, also representing both the joint constraints obtained by likelihood multiplication as well as hierarchical analysis. And the triangles represents the results obtained by likelihood multiplication, and the unfilled triangles represents the ones coming from the hierarchical analysis. And for this plot, the color code or the gradient of the plot corresponds to the redshifted median total mass of the binary system. And from these plots, we also see that our observations are all consistent with the GR prediction. Moving on to next slide. So the next type of analysis using the ring down signal is looking for the echoes. So if so we assume that the merger remnant is black hole, but if the merger remnant is not a classical black hole, but an exotic compact object which does not have an event horizon but a reflective surface, we expect gravitational emission as repeating pulses, and this is known as called as echoes. Now, in the figure here, you see two different scenarios. One is the black hole case and another is exotic compact object. And for a black hole, you have the ring down and you don't see any other anything else after that. But in the exotic compact object figure, you can see that after ring down, you see these pulses, and this figure is taken from a web page just to demonstrate this effect. Moving on to next slide. In this analysis, we search for these post-merger echoes in a morphology independent way using base wave algorithm, and we use sine Gaussians as wavelets here. And the main results of the analysis is the signal versus noise base factors, and we calculate these base factors for each event, and we also quantify this using their significance using the p-values for each event. So on the right hand side, we show the probability, the p-value plot for the obtained from this analysis for the O3b events. And these dashed lines corresponding to the null hypothesis, with the gray representing the uncertainty in the measurement at 90%. And you can also see these blue lines, which corresponds to the measurement obtained from the O3b events, with the corresponding uncertainties represented by this light blue region. And from this PP plot, which is when you compare these dashed lines with the solid blue lines, we can see that this PP plot is consistent with the hypothesis, that is the that is the dashed lines, indicating that we find no evidence for echoes. With that, I will hand it over to conclude this presentation. Thanks.
Thank you all for discussing this with us. So we told you a little bit about how we tested for deviations from general relativity using the 9 different methods presented. We found no statistical significant evidence for any deviation from general relativity. And we have updated the bounds on deformation parameters in the case of parameterized models and tests. And we computed joint bounds whenever possible, to summarize some of the results we found. And next, we're going to allow people to have a question and answer session. So people have already been typing. So if you haven't seen it yet, you should have a pop-out window with Q&A on it. And what we're going to do as people type their questions out, we'll ask some of the panelists to go ahead and speak about those questions. So keep asking as you will, and we'll be reading them off. The first question from Mark was that one of the slides back a bit, he thought showed boson stars. And he asked if boson stars have been observed. And Krishnendu is going to answer that question for us.
So there are theoretical models for boson stars, but we don't have any observational evidence as of now for the boson star models. That is the answer.
Sorry, I classically muted myself. Thank you, Krishnendu. And George asks, how do tests of combined polarization handle the uncertainty and precision of the orientation of the orbital plane in the line of sight? Isaac, will you take this for us?
Sure. So the method that we employ is based on null stream, so the method is basically based on the constructions of the null stream that from the antenna pattern function. And then the test is temporally agnostic about the waveform of the polarization mode itself. So so effectively that the test itself is temporally agnostic about, so we do not need to model the waveform, but what we test is instead which polarization subspace that the signal that we detected is on. So does this answer your question?
George, if you want some more follow-up, go ahead and ask another question, and Isaac can either answer it or type some more. Thank you. We have another question about how does the finite sensitivity of LVK at high frequencies affect the detection of gravitational wave echoes? So does one of the panelists take that? Maybe Anna, would you like to talk about this?
Oh, yeah, sure. So basically the finite sensitivity at high frequency doesn't influence that because we don't, echoes don't go to very high frequencies. The main difference is that we expect them at later time with respect to the main gravitational wave signal. So we don't have this frequency issue, let's say. We just look for signals at a later time with respect to the main signal and the ring down too.
Thank you very much. There's a follow-up question about echoes. It's a little bit further down that I thought I'd bring up now. But the question is, are we confirming that there is no evidence whatsoever for gravitational wave echoes, thus invalidating any possible claims made so far?
Okay, so I'm not sure how to answer this, but with our model, we did not see any echoes in the events of O3b because this was a new pipeline, and therefore we applied it only to the new events of O3b. We didn't use this specific pipeline on previous events. So what I can confirm is that with our method, we did not see anything with these new events.
Thanks, Anna. And just know if any of the other panelists or speakers want to jump in at any point, please do. As I read. So Mark asks if for exotic objects ring down gravitational wave. Okay, sorry. So is it possible to determine mass radius of the reflections from Remnant? I guess that's you again, Krishnendu, unless someone else wants to talk about the possibility of this. Does anyone want to speak up about the possibility?
I think, sorry, dear, I was muted.
Oh, sorry.
Ring down gravitational, is it possible to determine? I'm not sure if I know the answer actually. Maybe somebody else wants to answer this question.
So I know there are people who are working on models, for example, for echoes. So it's also some ring down signal from exotic objects. So I think that maybe you can find some relations, but I'm not an expert at all on this. So I can't give a specific answer.
That makes sense, though. I mean, our ability to measure a parameter well, even in traditional ring down of a Kerr-Einstein black hole, is dependent on the fact that we can model the parameters well. So I think that sounds reasonable, Marta. Thank you. And Marta, while we have you on the line, there was a question about the analysis of the neutron star black hole event, and you were starting to type an answer, and I thought you might as well share it with us.
Yes, I can take this one. So yeah, we don't actually include tidal effects in the NSBH, in the analysis of the NSBH in this paper, because we consider all sources to be BBH in the parameterized test that we presented. So in this specific case, the tidal effects are actually suppressed by the mass ratio of the source. And in fact, even in the discovery paper, there were no significant tidal effects that could be measured. So the bottom line is that we just treat this one as a BVH.
Thank you, Marta. So I think echoes is a popular topic today because there's a further question on echoes about how many free parameters are there in the morphology independent echo models. Does anyone know the answer?
Yeah, so the first thing is that we're not really using a model. What we're using is bias wave, which uses some wavelets, which are basically a sort of combination of some Gaussians, more or less. And these wavelets have some parameters. If I remember correctly, the basic bias wavelets have 4 parameters, and we add 5 more to account for echoes effect, like the time of the first echoes and the difference in time between the different trains and the widening factor, such of that. So I think that in total we have 9 parameters by these wavelets, but they're not like if 3 parameters of a model. It's not like parameter estimation. It's a bit different.
Thank you. We appreciate your answer. There's one other question from Mandeep, which is funny because it's indicated as a rhetorical question, and I'm not sure if people want to answer it, but I find it an intriguing question. And since we're at almost the end of the hour, I thought it would be a kind of nice one to end with, which is how do we all feel about no deviations from GR so far? And are any of us sad? which I think, does anyone feel inclined to express their own personal opinion about this? It's too scary of a question. I find it that, you know, I had to learn to say to people that we're not trying to prove Einstein right, if you want to be colloquial about it, but really prove Einstein wrong, because that's how you go about testing a theory. You look for evidence that something is different than you would have predicted from the theory itself. So I guess it's not, sad as a strong word, but the fact that everything's been consistent due to the quality of the data, and at some point we're actually going to get to the quality of how we've been predicting Einstein's equations, so that the quality of the theoretical predictions will start to also matter as the detectors improve, isn't maybe too surprising. I don't think it's not over. This is why we keep having to do this. As we get better and better data, we will continue to challenge our understanding of the theory of general relativity and see if it's the correct interpretation of gravity. So maybe if it kept happening after the detectors get better, I would be sad that we didn't find any smoking gun of something new to learn about the universe and gravity's role. But that's just me. So I'll see if anyone else wants to say anything. Or any closing remarks, since it's 2 minutes to the hour. Oh wait, there were another question that I didn't. Santos asked if gravitational speed is the same as light or what, and people are answering there. But if you want to answer live, feel free.
Yeah, I was just typing that with the signals that we have observed so far, there does not seem to be any evidence that they are different. So that's the most correct way to frame an answer for that.
Yes, and there's been, you know, it's been lovely. The first Binary Neutron Star event obviously was sort of the thing where we all learned about how exciting it could be. So thank you very much. Is it possible to expand the Einstein's equations to a parallel universe? Oof, I think that one might be a little tricky to answer. Is it possible? Parallel universe is kind of a funky concept, so we might have to type an answer on that one. All right. I think, yes. So are the slides available in document form? Can someone answer that? Are these slides going to be available to the public?
That's certainly been the practice for all the other webinars. So I've just make the DCC link public afterwards, and we can put that out on social media so that people can follow up.
Thanks so much, Martin. So the answer is yes, you will be able to find these slides. So keep monitoring your social media sites and you will be able to find them soon. So I guess at this time, we'll wrap things up. And I first thank you to the audience for coming and being excited about tests of general relativity and all the LVK exciting results, and also to all the people who are here from many different countries in the world, many different time zones. Thank you for doing your best to both reveal the exciting results we have so far from this paper and answering the questions cold, which is always hard to do. Thank you very much, guys. So anything we should close with, or is this a traditional thing, Martin and Tonya?
No, I think you've done your duty, covered all the bases. So yeah, thanks everyone. And we'll be along with more webinars next month. Details still be worked out, but again, watch out on social media. There'll be more webinars coming in February.
Thanks everyone. Have a good rest of your day.